My name is Paco. I'm from Databricks. I'm Director of Community Evangelism at Databricks, so I'm the evangelist for Spark. And as Ben had mentioned a little bit earlier today, the Spark project grew out of Mesos. Actually, I've heard this story. I'd like to get it confirmed, but apparently some of the folks flew back to Ben's home and were watching Firefly every night as they were developing Spark when this first started out. So I've heard some stories about the origins there. Anyway, I'd like to present about one of the frameworks that's been on Mesos for a long time, Apache Spark, and give some background on it, because I kind of figure like a number of folks in the audience probably haven't seen too much of Spark before, but we are catching a lot of adoption. And also I'd like to talk about how and why this really fits with Mesos. So in terms of a little bit of history, first off, we're kind of at what I would characterize conservatively as hypergrowth. We've hit this mark where every time we have a major meeting about Spark, it's doubled in size. And the number of committers, the number of contributors, et cetera, as far as the Apache project, it's kind of phenomenal. Spark went into Apache earlier this year and went to a top-level project right away, and then subsequently had a 1.0 release very quickly. But I want to go back and show a little bit of background about what this is and why this is. And so a bit of history, maybe 80 or so years of history. Back in the 1920s, 1930s, there were some people working out the math of what could be computed. And so Haskell Curry, you've probably heard those names before, but definitely Alonzo Church working with lambda calculus, combinators, et cetera. And it was an interesting challenge because they didn't have computers to work with. But they came up with this math. And about 40 years later, people like John Bacchus, who had led the Fortran team at IBM, or David Turner, who did a lot of the math that gets used in compiler theory, database theory, et cetera. In the 70s, these people took that math and applied it for parallel processing, really working towards functional programming languages that could leverage the math for parallel processing. And that was good. Anybody else ever programmed in FP here? I had to do FP in grad school. Maybe a couple of people. OK, good. Well, it wasn't the easiest thing to work with. But things like Scala and others that are descendants from that, of course, built upon it. Now, about 20 years after that, there was a really interesting inflection point where I would point to projects like Firefly. I mentioned Patty Mize here. People started looking at moving AI, moving machine learning for different types of applications, moving it away from just some sort of super smart program running on a machine and putting the smarts into web apps, and then collecting a lot of log data off of social interactions with the web apps, and using that log data, aggregating it to build machine learning products that could make the web app smarter. So you got a kind of virtuous cycle, and a lot of machine data that led directly to big data. But again, that was a really good reason for wanting to have a lot more parallel processing, a lot of horizontal scale out, and functional programming came into play. And what I point to is if you read the original paper about MapReduce at Google, they make a big point about how they had borrowed ideas from this long history of functional programming to be able to do fault tolerance at scale. MapReduce came out of work in 2002, so that's 12 years ago. The paper came out in late 2004, and on, hit a lot of nice growth. Spark started out in about 2009, and one of the main papers was published about 2010. So it came out really, it's hitting its inflection about a decade later. And that's an important point because there have been so many changes that have happened in data centers over that decade. Certainly rolling the clock back to 2002, you didn't have multi-core as commodity. You didn't have SSDs. You didn't have a lot of things you would sort of expect in today's class of commodity hardware. And meanwhile, the spinny disks themselves haven't really changed a whole lot. So we see a very different kind of economics in data centers, and Spark is trying to address that. And the idea is that looking at MapReduce, there are a couple of troubling problems with what you see in the MapReduce API in Hadoop when it's moved into production. Number one, and I've felt this as an engineering director over the years, it's difficult to hire a lot of people who are really expert at writing directly in MapReduce. And number two, even if you do have that expertise, you commonly run into a lot of different types of performance bottlenecks. Or it may just be that a batch window doesn't really fit your use case. So consequently, even though Hadoop has become really popular for big data, there's a lot of other kind of specialized systems that came up as well. So we can do a lot with batch, but then we also want to go and do graph. So there are things like Priggle leading into Giraffe, or we want to do some kind of large-scale SQL. So there's things like F1 leading into Impala, or stream processing, things like Millwheel leading into Storm, et cetera. Specialized systems also have a lot of overhead in terms of you have more clusters to manage, more inventory in terms of your ops overhead. But in general, it's kind of like the idea of static partitioning that we've seen in the talks earlier today. If you've got a number of different frameworks that are all doing their own specialized parts, that's analogous to having a static partitioning on a cluster. Kind of at a different level conceptually, but much the same effect and much the same problem. So Spark is a way of generalizing what MapReduce had done by really just changing two things. One is to take advantage of a lot more memory that's available and really focusing on the compute right in memory. And number two, when you're specifying a program, as the program runs, it builds up a graph of what's going to be computed. It's a directed acyclic graph, a DAG, and there's lazy evaluation on that. So even though the program runs, it doesn't necessarily compute things right away. And by leveraging both the cache and the DAG, we're able to get fault tolerance and parallelism. So the idea with Spark is to be able to handle a variety of different types of use cases. Again, pulling all those specialized systems together, taking care of batch, taking care of interactive, streaming, doing graph processing, machine learning, SQL, et cetera. And the effect was to remove some of the synchronization barriers in Hadoop so that you could take advantage of more memory, basically more pipelining of your big data applications without having to continually bring your data up from distributed file system into memory, map, then shuffle, then reduce, and drop it back down. Instead, you can pipeline through with a long chain of processing. Now, one thing about Spark, when you look at the code base, if you were to compare the code that's required for MapReduce in Hadoop, along with the code that's required for streaming in Storm, SQL in Impala, graph processing in Giraffe, you put that all together, it's about a 7-to-1 ratio compared with what's in Spark. And the idea is that Spark provides a unified engine underneath, but these other types of features are actually just relatively small libraries built on top. So I want to show a little bit about the dynamics, and then I'll show a little of how Spark works. We have a framework. In Mesos kind of context, Spark is a framework. And so the framework has a driver program. Essentially, the client would be analogous in Hadoop. And we've got some sort of Spark context that manages our dependency injection. Basically, keeps track of where the Mesos master and other resources are. And then we've got worker nodes out on the cluster. We've got executors out there. They're managing the tasks. They're managing the data that's cached, et cetera. And all of this is built to support something called RDDs, resilient distributed data sets. It's the foundation inside of Spark is that you've got some kind of partition data, and you've got this abstraction, an RDD, and then you can apply a lot of functions to the RDDs to get the results that you need. These could be coming out of collections in a language like Scala or Python or Java, wherever you've got your collections defined. You could parallelize those as RDDs, or they could be coming out of some sort of data set in S3 or HDFS, other types of distributed file frameworks. I mentioned about lazy evaluation and having RDDs, this base abstraction. And the idea is this. I can define, I want to pull in some data. I've got an endpoint of data, say it's an HDFS. So I'll define that I'm going to read that. And then I can define some maps and some filters and some other types of things that I want to do on top of that data. Nothing happens. It just builds up a graph. But that graph is really important because that gets serialized out to the cluster. And so for every partition of data, it knows how to recompute to rebuild the results that you need. And this is really critical because the difference with Spark is that you're really leveraging memory. Now, in Hadoop, the idea was to leverage spinny disks and get better fault tolerance. That's what Google needed with MapReduce. And the idea is that spinny disks fail at a certain rate. And so we came up with systems like HDFS that have replication, and we leverage that for fault tolerance. Up in memory, though, it's being proven that replication is not a good trade-off. A better trade-off would be to recompute the graph, to do recomputation. And so that's what RDDs are based on, basically a different kind of trade-off based on where you're at inside of the architecture. So there's a lot of transformations on RDDs, again, functions. These are lazy, but then when you actually need a piece of data, it'll trigger that computation. And that's great, because if you lose a node, then you can just go and grab a copy of the data that was on that node, reapply the graph, and come up with your results. And there's also a notion of working set, that of course, we're trying to keep a lot of data in memory, but you don't need to keep all of it. And if you have this graph, a lot of your computation can be collapsed down into combined operations, so you don't need to keep a copy at each step there. Anyway, we have an LRU, and so we're taking a look at when the different RDDs were being accessed most recently. The ones that weren't accessed most recently, of course, will be evicted out. So you get a kind of working set behavior, a graceful degradation between either having everything you can run in memory or having to do some spills out to disk. And it's a lot different than in Hadoop programming, where you have to explicitly manage your spills. OK, so real quick, I just want to show a program and kind of animate how this works. But if I have a bunch of log files out in HDFS, and I want to start carving them up and come up with a count of how many errors were due to MySQL, how many errors were due to PHP, then here's a really brief program. Now, the interesting thing is that these first 3, 4 lines of code, when they're run, nothing happens. All it does is build up a graph. So basically, the first time that something happens is when you've got an action, when you actually need to aggregate the data. Here, I'm going to get a count of how many errors were due to MySQL. Then those actions trigger the computation. And what happens is we've got a driver, several different worker nodes, and out in the worker nodes, we've got different blocks of data. So the graph gets serialized out, and these workers will go and do their processing from HDFS and stick the results in cache, and then send the partial aggregates back to the driver as requested. You get the count back. But the magic happens is that when you have another action later on down in your graph, you don't have to go back to HDFS again. You can leverage what's in cache and then just send the results in, and then get a couple orders of magnitude speed up, hopefully. So it's a lot more of a pipelining effect. The other thing about Spark is trying to handle a lot of different types of use cases. So a typical architecture, you would have, say, Mesos distributed kernel, HDFS on top of that. Tachyon is also part of the Spark project. It's like an in-memory distributed file system. The commands look much like HDFS, but it's all in memory, off heap, all memory speed access. And then having Spark, but then up above, you could have Spark SQL. You could do real-time analytics and Spark streaming. There's a machine learning library called MLlib, and also a graph query engine called GraphX, which is basically, it's like the GraphLab API. The idea is to be able to run all of these on top of a common engine. OK, so just to show real quick, and I'll kind of wrap this up maybe for some questions. Spark SQL, basically, I can take any RDD, and I can register it as a table, and then make queries against it. Or I can create a context out of, say, a Hive metastore, and then access that as an RDD, and apply functions to it. So I can go back and forth between SQL and functional programming. Spark streaming, also with I take my Spark context, and I define a I define a window on it. Here, this code is showing like 10 seconds. So I'm doing micro batches. Every time period, I collect the data into an RDD, apply my processing, and then I can take that RDD and store it someplace and process it later, perhaps. MLlib, machine learning, it's also a similar kind of thing. You have vectors of data as RDDs, and you can train models off of them. So here's an example, like 4 lines of code to train and test k-means clustering. And also GraphX. It's basically inheriting a lot of the functionality of, say, GraphLab, but still on this same RDD abstraction. I can have one data structure that describes my vertices in a graph, and another data structure that describes the edges between them, and then I pull them together into a graph and start applying functions. Okay, so there's a lot of things that you could do with Spark, but it's not really one size fits all. And this is the case for multi-tenancy, is that we're seeing patterns like this out in the field where people will be managing a lot of the plumbing coming into something like Spark with Kafka. And you're running your big compute in Spark, but then it's also good maybe to have some kind of key value store for storing some of your partial results, things like that. So Cassandra might be very indicated. And then the results are going to go out to maybe dashboards or some kind of search or a web app. But there's a lot of reasons for having Spark being integrated with other types of apps, and this is a great reason for being able to run it on top of Mesos, also a great reason for being able to use Docker, to be able to containerize these. I've got in the slides here a few different case studies, some from Twitter. I'm not going to go through them, but they'll be there if you want to follow on these links. Twitter, eBay, Yahoo, and also a machine learning one from Spotify, where they recently did a cutover from Hadoop to Spark, and they talked through the steps that they had to go through. And I'll also add a couple of points here. We do have a very active community. Definitely the mailing lists are the best resource for developers, and all the Spark committers are daily engaged in the email lists. We also have Spark Summit that we do on East Coast and West Coast now, so we do this twice a year, and that's been growing very fast, but we have all the slides and videos from the past Spark Summits are archived, and they're probably one of the best resources for being able to learn about this. We also have Spark Camp and some other workshops that are going out. TypeSafe and Big Data Partners and others are starting to do workshops as well. And there's a few books out about this too. But the main thing I want to underscore is this. We're seeing a lot of interesting specialized systems like Storm, for instance, can be replaced with Spark Streaming in a lot of cases. So we're seeing a move to try to unify these applications just to use a common engine, but then tie it into things like Kafka, Cassandra, et cetera. There are a lot of trade-offs in terms of how much memory a particular app is going to need, how much disk, how much network, et cetera. So the idea of being able to containerize that and be able to manage it in a Mesos context, it gives very fine-grained control. And in fact, if you look through on the Twitter use case, they make a pretty interesting comparison between their use of Mesos and Yarn. Okay, thank you very much.